Section 8.5, this is day 81. The topic is partial fractions, and it's extending something that you learned in your pre-calc class and showing how it's useful in calculus. So we're starting with a polynomial over a polynomial, and we have the antiderivative. Turns out that the denominator factors. So if we can take this factored and split the numerator into three different values so that I can take apart this rational function, then we can take the antiderivative of each of these terms individually. So the process is take a over the first factor, b over the second factor, and c over the third factor, and multiply the right side by this denominator here. Well, when I bring this denominator up, the x's cancel, and I've got a times the other two factors. When I bring this up, the x plus 3's cancel, and I've got b times the other two factors, and then the same thing with c. So now what I've got is a long statement, and if I pick three convenient values for x, lots of stuff disappears, and finding the coefficients a, b, and c are pretty easy. So first time around, I'm going to let x equal 0. That way this term here and this term here disappear. 0 times anything is 0, and I've just got 0 plugged in here, which is -9, equals 3 times -1 times a, or -3a, and a equals 3. So right there. Second time around, I'm going to let x equal 1. That's going to force this first term and this second term to disappear, because the 1 minus 1 here forces all that to be 0, and 1 minus 1 here makes all that 0. So plugging 1 to the left side and 1 in over here produces 8 and 4c, which leaves c equals 2. And then finally, for the last factor, if I let x equal -3, this is going to disappear and become 0. The last is going to become 0. And now I've got plugging in -3 here to get 12b. Plugging in -3 is a little bit of work, but you can figure out pretty quickly that it's -12. So b equals 1 or -1. Looks like it should be -1, so I'm missing a negative sign there. Let me throw it in. b equals -1. Okay. So moving on, now that I've figured out what a, b, and c are, I can take this rational function, rewrite it as these three, and then the antiderivatives are very quick. 3 times the natural log of x minus the natural log of x plus 3, and then 2 times the natural log of x minus 1. All those combined using log properties produces this final answer. Second example is going to be very similar to the first. Take the denominator, factor it. We have two terms, so I'm going to have two fractions, but what's different here is we have a quadratic term. So this quadratic term produces a different numerator. It's going to be ax plus b over x squared plus 4. And then the second factor is linear, so it's just going to be c over 2x minus 1. The difference between those two is listed up here. Linear factors look like this, and be careful. This is still considered a linear factor, but it's a repeated linear factor. So I've got x plus a number squared, which is different than saying x squared plus a number over here. So you'll see a repeated linear factor in the third example, which doesn't fit here. We'll put it on the third page. So anyway, back to the second example. Bring the denominator up to the other side. We have ax plus b. The x squared plus 4 cancels, so only 2x plus 1 is left behind. And when I bring this up over here, I've got c times x squared plus 4. So we're going to continue on and plug in 1/2 to make this equal 0, which leaves me with 1/4 plus 4 times c. Plugging in 1/2 over here produces 1/4 minus 1/2 minus 21, which is -85/4. Solving that, multiply both sides by 4 to get whole numbers, or integers actually, and then how many times is 17 going to 85? Turns out it goes in 5 times. After that, there's no other roots that work because x squared plus 4 doesn't have any real roots. So now we need a different method. So what we're going to do is we're actually going to multiply this out, and we're going to compare coefficients. So left side stays x squared minus x minus 21. Right side becomes 2ax squared minus ax, etc., etc. And you can see how that's the remaining terms there. And now what we're going to do is we're going to look at the quadratic terms. So everything with an x squared in it was highlighted in light green. On the left side, the coefficient of x squared is 1. On the right side, the x squareds have coefficients of 2a minus 5. So I have 1 equals 2a minus 5, and that tells me that a is going to equal 3. Doing the same thing with the number values, okay, and I skip the x's, and I'll tell you why in a second. If I do the same thing with the number values, -21 is a number, b is a number, and we have negative 20 over here. So when I set those three things equal to each other, we have negative 21 equals negative b minus 20. Solve that and we get b equals 1. Now the reason why I didn't do anything with the linear terms, the x terms, is because if I look on the left side, I have negative 1 there, but on the right side, I would have negative a and a positive 2b. And solving that involves both the a and the b variables, and I just thought it's a little bit easier to work with the constants and not the linear term. But if you wanted to, you could do the linear term. Since we already know that a is 3, we could plug that in and solve for b. But there's more than one way of doing it. Anyway, now that we've discovered what a, b, and c are, our original rational function breaks down into these two separate functions, 3x plus 1 over x squared plus 4, and then a negative 5 over 2x minus 1. The antiderivative of this first one needs to be split again so that we get 3x over x squared plus 4 plus the antiderivative of 1 over x squared plus 4, and then minus 5 times the antiderivative of 1 over 2x minus 1. And I've run out of space to put the answer, so I'll have the answer on the next slide. So there wasn't enough space on that previous slide. You might want to just finish the notes for this day on this page here or someplace else in your document. In any case, to finish the previous example, the antiderivative of those three, doing a u substitution, the first one is 3/2 natural log x squared plus 4. The second one is actually an example of inverse tangent with u equal x and a equal to 2. And then the last one again is another natural log statement. So there's your final answer, and don't forget about your plus c. So in the last one, we have what's called a repeated linear. And what happens with that is that because we have x plus 3 to the second power, some of the numerator can come from that denominator written once, and some of that can come from that denominator as it appears over here. So with repeated linears, you decrease the exponent and build up until you hit the exponent that you see. We only have x squared, so we're only going to need 2. But again, the process is the same. Take this x plus 3 squared, bring it up into the numerator over here. One of the x plus 3's will cancel, and I'm left with a times x plus 3. For the second fraction, x plus 3 squared over x plus 3 squared completely cancels. I'm just left with b. So what I'm going to do is I'm going to expand this out and then look at coefficients. In front of the x's, I have 8 on the left side and a on the right side, so a equals 8. And for constants, I have 3 on the left side and 3a plus b. Well, I know that a is 8, so I'm going to wind up with 3 equaling 24 plus b, and b is negative 21. Now that we found a and b, we're ready to do the two separate antiderivatives. The antiderivative of 8 over x plus 3 is again a natural log with 8 out front, and then move 21, and you wind up with a u substitution because the exponent of the denominator is 2, so it's not going to be a natural log case like the previous one where the exponent of the denominator is to the first power, which would make it negative 1 in the numerator. In this case, the exponent of the denominator is 2, so if you do a u substitution with u to the negative 2, your final answer after you take the antiderivative is negative 21 times negative 1 x plus 3 to the negative 1, and then throw in your plus c at the end. There's your final answer. So that's partial fractions applied to antiderivatives. See you in class.